Hi, I am Shahnaz. In last lecture we did covering maps and covering spaces, and we did some results about covering maps. Now let us begin this lecture with the following lemma. So let us consider a path P, a map P from a space X to Y, which is given to be a covering. Let us recall what do we mean by a covering. So if we have two spaces X and Y which are given to be topological, then a map P from X to Y is said to be a covering, and sometimes we call this map a covering projection. So if for each point Y in this capital Y we have an open neighborhood, say V, which contains this Y, such that this P inverse V, it is the disjoint union of open sets in X, such that this P restricted to these UIs, and they are homeomorphisms. So let P from X to Y be a covering. Then for any Y, in Y, P inverse Y, this is a discrete set. So let us prove this. So let us choose this Y in Y. Let Y belongs to Y, and P from X to Y be a covering. Therefore for this Y in Y there exists an open neighborhood, say capital V of Y. Therefore there exists an open neighborhood, say V of Y, such that P inverse Y, this is disjoint union of UIs, where this I is in the I, where this capital I is some indexed set. So these capital UIs are open sets in X, where UIs are open subsets of X. With the property that, so with the property that when we restrict this Pi to these UIs, which is a map from UI to V, this is a homeomorphism. Now these Pi's being homeomorphism means they are bijective maps. That means if we that means for each xi in ui, so this implies that for each I there exists a unique xi in ui such that Now one can note here this v, this v contains y, so it is like this. That is, so this is over space y, and this is the covering space of x, and these are these ui's, u1. So here we are taking these discrete, they may not be discrete. So y, this is v, and y is contained in v. Now corresponding to this v, the inverse image of v are these open sets. So in each ui's there must exist a unique xi for which p of xi is y, because this p when we restrict to this p to these ui's, these are homeomorphisms, so they must be bijective maps. So this imply that for each I, there exists this unique xi in ui such that p of xi is y. Note here this unique is due to the homeomorphism, because when we restrict this p to ui, this is a homeomorphism, hence an injective map. That is why this unique shows up here. Now let us consider this set. Therefore p inverse y, it contains precisely these elements xi, where I is in I. Now we have to show that this set is a discrete set. Now it is given that each ui is open in X. It follows from the definition of subspace topology that each xi in the inverse image of y is an open subset of p inverse y. So let us mention this here. Since ui is open in X, it follows from the definition of subspace topology, it follows from the definition of subspace topology that each xi in p inverse y is an open subset of p inverse y, is an open subset of p inverse y. So let us mention this here. So by subspace topology we mean suppose we are given a topological space X, and this is the collection of open sets, this tau. Now let A be any subset of X. So if we look at these sets A intersection say Ti, where this Ti is contained in this Ti is an element of tau, then these are obviously these are open subsets of A, and this forms a topology on A, and that is called a subspace topology of X relative to A. Now note here, these UIs, they are open subsets of X, and this P inverse UI intersection, sorry, this P inverse Y intersection these UIs, this is precisely the singleton set Xi. So that means these sets, they form open subsets with respect to this set P inverse Y. So each Xi P inverse Y is an open subset of P inverse Y, but the subspace topology on P inverse Y is just discrete topology. So let us mention this here, but the subspace topology on P inverse Y is the discrete topology. Put differently, this is equivalent to saying that P inverse Y is a discrete set. So this is equivalent to saying that P inverse Y is a discrete set. So if P is a covering projection from X to Y, then if we choose any point here Y in Y, which is in the open neighborhood V, then P inverse Y is always a discrete set. Now let us define path liftings. So suppose we have a space X and a space Y. By space we mean these spaces are topological, and this is the map P. Suppose we are given a path, say from interval AB to Y. This is our path F. Now the question is that can we lift this path F to another path, say G, such that this diagram commutes, i.e. such that this composite map P composite G is F. If such a map G, that is why, so it is not necessary that this map G exists, but whenever this map such a map exists, we say G is a lifting of F. So that means this path F is lifted to path G. Now this is with the following condition. Suppose there is some X in X such that F of A is P of X. That means this path F, this starts with point FA, which is P of X. So as long as we know where to start this path G in X, we are done. So this path is lifted such that this G of A is equal to X. So this is the initial point for the path. So this lifting is with these conditions, i.e. there is some X in X such that F of A is Px and G of A is X. So that means if this is the space X here, this is a space y here. So suppose this is the interval AB here, and this is the path F here, with initial point F of A and final point F of B. Now we can lift this path in this space such that, so one must know the initial point where this path is started. Now we know that between these two spaces we have the map P. Now P is such that there is some point x in X such that P of X is mapped to this point. Now this path is lifted such that it starts with this point X here. So this is the lifting of this path in this space. So let us define this first. So we have the following definition. Let us consider a map P. Let P from X to Y be a map. So indeed these X, Y are topological space, and this map is a continuous map. So between topological spaces, and let F be a path in Y. Let X in X be any point with the condition that this F of A is P of X. So a path, say G, from interval AB to X, this is called a lift of F. This is called a lift of F with the starting point this X here. So with the starting point X, that means this, with the starting point X, that is if this G of A is X, and this composition map POG, this is F. So this is same as to say that this diagram commutes. So this is the space X, this is the space X, this is the space Y, and here we have this map, say it's the map P, and we are given a path in Y, which is the path F. Then we say this path F, this path G is lift of F if this diagram commutes. So let us mention this here, i.e. if the following diagram commutes. So these are called commutative diagrams. Let us give an example of path liftings. So let our X be the set of real numbers and this space y be the unit circle S1. Now define a map. Say P from R to S1 as this P takes this point T to the point e power it on the unit circle, and let f from say interval 0 to b be a path given as, so this f takes this point t to e power 2it. So its starting point, obviously when we put 0 here it is mapped to 1, so with starting point f of 0 which is called 1. Now let us pick a number, say let x be this real number 4 pi, which is a real number. Then one can know that then so this is over a real line, this is over space y which is S1, and this is the map P. Now let us suppose it's the point 1 here, I mean it's 1 comma 0. Let us notice point by 1 here. So and this is the map f here. Now f map is this point 0 to this point 1, so this is same as f of 0. Now we have to pick a point here, say x, whose image under P is this point. So let us choose this x to be equal to 4 pi. So this point is not unique, so we can lift this path which can start to any point which is say multiply of 4 pi, which is obvious multiply of 4 pi. So if we take this p of x, that is p of 4 pi, and p of 4 pi is same as here, this is e to the power 4 pi I, and that is 1. So this is same as p of x, which is 4 pi. So then p of x, which is p of 4 pi, and that is equal to 1, is same as f of 0. Now let us lift this path. So this path is actually any segment here. So this is, so if it is the path, so this is f0, and this is f of b. Then we can lift this path to a path here which starts at this point 4 pi. So this path starts here. So this path starts here. is a path in the real line, so we can lift this path to here. So one can note here, so let us denote this path G here. So let G from 0 to B to R be such that G takes this point T to 4 pi plus T. So obviously this 4 pi plus T, when T is 0, this is 4 pi, and when T varies here in this interval, this is the path here. Also, if we compose this path, these two paths, POG of suppose T, this is same as P of GT, this is same as P of, now G of T is 4 pi plus T, this is e to the power 4 pi I plus T, sorry 4 pi plus T times I, and that is e to the power 4 pi I plus Ti, and that is e to the power Ti, which is same as f of t. So one can note here these maps commute. So this is actually a lift of path F to path G.